Okay, I'm going to try and be brief because I know you've done some of this in the past. We're going to look at acids and bases. I have, on purpose, put the math portion first, even though I wouldn't normally do that, just to make sure that you get the math information and you can do the math calculations first, and like work on your worksheet. And then it talks in a little bit more about what acids and bases actually are. There are different ways of defining them. So that was on purpose. So acids and bases are solutions, just like the solutions we've been talking about for, gosh, quite some time now. They have a couple of key features that sort of help to distinguish between them. Acids tend to taste sour, so things like lemon juice, vinegar, those are acidic, so they taste sour. They turn litmus paper red, actually. That's crummy. So from blue to red. And then they can react with active metals. So you've seen earlier this year zinc for sure reacting with hydrochloric acid to make the hydrogen balloon, for instance. They react with bases to make water and a salt. Bases taste bitter. So I think coffee is a little bit basic. There aren't really a lot of bases that you should taste off the top of my head. And the reason that those are crossed out is because, of course, in a lab, you should never taste anything. They turn litmus paper from red to blue. They feel sort of slippery, so if you've ever used some sorts of cleaners like ammonia, it's a little bit basic. So if you've ever gotten like Windex on your hands, it feels kind of slippery. And then they react with acids. And bases plus acids, whoops, that was a silly pen to choose. Bases plus acids equal water and salt. Depending on, of course, the identity of the base and the acid. And we'll talk about how that works in a little bit. So if we look, just as we've talked about other solutions like salt solutions, if you were to shrink down very small and look at a solution of acid, you would see water molecules, and then you would also see, at least initially, these HA molecules. H stands for hydrogen, A stands for acid. So this is just any sort of generic kind of an acid. And so when you initially add it to the water, everything is together, you have these HA molecules. Then what happens, just like as happens with some other solutions that we've talked about, some of them will dissociate. And the amount of dissociation is going to determine what sort of an acid it is. So strong acids, of which there are 5 that you need to know, I believe, they dissociate 100%. So if you notice, in this beaker, there are no HA molecules. There are only H plus and A minus. So 0. Okay, I'm going to say there are 20 of these, and there are likewise 20 of those. Because they have to stay equal because each HA splits into one H plus and one A minus. If this was an acid like H2SO4, then you would have 2 H's for every one SO4. So it's a similar thing to when we talked about ionic compounds dissociating back when we did like solubility rules and double replacement reactions. Yeah. So these acids are strong acids because they dissociate 100%. That is what a strong acid is. It doesn't matter if it's concentrated or dilute or whatever, it just dissociates 100%. Weak acids, which is like every other acid than the few that I'll tell you for strong acids, they dissociate only a small amount. So in this case, if we started out again with 20 HA, I'm going to say we have like 17 HAs left, and then 3 of each of those. So while our strong acid was highly conductive, it was a strong electrolyte because it had lots of ions, this is going to be very not so conductive. So it will have a little bit of conductivity, like greater than just water, but not very much. So if you think back to the lab that we did, the electrolytes lab, you had one that you tested that was a strong acid, I think it was HCl, and then you had a couple of other acids that were weak acids, and their numbers were much lower. So here you see some strong bases and acids, and then just a couple of examples of weak acids and bases. So the acids, I guess there's just 3 that you have to know. That's nice of me. So hydrochloric acid, nitric acid, and sulfuric acid, those are 3 common strong acids. And strong acids, they're kind of like, they just are. So it's not, you don't have to like figure out if something is a strong acid. It either is on this list or it isn't. HBr and HI are also on this list. Those are a little less common, so you don't need to know them. But, oops. But just FYI that they are on that list. There's a couple others that we don't use ever. And then a lot of the OH bases, like sodium hydroxide, potassium hydroxide, they are strong bases. So they dissociate 100% when they're dissolved. Weak acids and bases are almost, like, there's almost an infinite number. A couple that we talk about from time to time are this first one, which is acetic acid. And the reason the arrow is pointing at this H is that that is the H that is the acid. It's the one that leaves when it dissociates. So it'd be CH3COO minus plus H plus. NH3 is ammonia, which I talked about at the beginning. This is what's in Windex that makes it like slippery. It is very interesting because as you see, it doesn't have an OH. So we'll talk about why that becomes basic after we talk about the math. So, does your water conduct electrical current? You might remember, again, from the electrolytes lab, that it is a very weak electrolyte. It conducts a teeny bit of electricity. And the reason that it conducts a teeny bit of electricity, and it's actually a very specific amount, is that when you have just plain water, in a cup or a jar or a beaker or whatever, wherever it is, there's always a slight amount of dissociation. What happens is that the H and the OH separate a very small amount. And because the O is pulling all the electrons to itself, one of the H's comes off from time to time. And it happens at a very specific amount. So if you were to take the concentration of the H pluses times the concentration of the OH minuses, which are equal in pure water, you would end up with 10 to the negative 14. Because in pure water, the little brackets mean molarity, by the by. It's just another way of saying molarity. So the molarity of hydrogen ions is equal to the molarity of hydroxide ions, because they're both coming from a single water molecule. And they each have a molarity of 10 to the negative 7th molar. So that's at 25 degrees C. That is neutral. The water, we know, is neutral. And so that is how we get the pH of 7, because pH is the negative log of the hydrogen ion concentration. So if you take the negative log of this, you end up with 7. So that's where it comes from. Once you start adding things into your water, you're going to shift this balance. And so that's why we get sometimes a higher hydrogen ion concentration or a lower hydrogen ion concentration and a higher hydroxide concentration. So to calculate the pH, use your calculator, and it's just the negative log of the hydrogen ion concentration. So it is a log-based scale, which means for every step up on the pH, that means it's a 10-fold increase. So a pH of 1 is 10 times more acidic than a pH of 2, and so on. Look at the examples. Hopefully you remember this from last year. At least a little bit. You can also work the other direction and solve for H plus, the hydrogen ion concentration. So if you know the pH, you just divide by -1 to get the negative over here. And then the opposite of log is 10 to the. So if you do 10 to the minus pH, you get the hydrogen ion concentration. So this is basically what this whole steppy thing is. It's just 10 to the minus pH, which is actually this line right here. So that is kind of the critical piece mathematically that you need. It's fine if you just remember, negative log of H plus and then 10 to the minus pH, if that works for you. Otherwise, you can go through the steps. That's fine. For POH, it's the same, just the opposite. So H plus and OH concentration always stay in balance. They're kind of like on a seesaw. So when one goes up, the other goes down, and vice versa. So sometimes if you're dealing with a base, say sodium hydroxide, it's easier to calculate using the OH concentration. So maybe you find the POH. And then there's a relationship between pH and POH, which is that when added together, they equal 14, which comes from the relationship we saw a little bit ago that the H plus concentration times the OH minus concentration equals 10 to the minus 7th. If you just negative log all of those, you get that. So that's kind of a nice way of going between pH and POH rather than using the concentrations. So here's just a little calculation map, I called it. It shows just sort of how you can compare and get from one quantity to another. So for instance, to go from pH to POH, you take 14 minus the pH. To go from POH to OH minus, you take 10 to the minus POH. And here antilog equals 10 to the, because I believe it's a different button on your calculator, and sometimes that confuses people. The KW that you see here, that is just the 10 to the negative 14th. That's the natural amount of dissociation in water. So if this is helpful, terrific. If it's confusing, totally ignore it. Okay, so that is all the calculations for now anyway. So if we're talking about acids and bases and calculating information about acids and bases, we need to have some information about what an acid and base actually is. So the definitions of what makes an acid and a base is, it sort of gets more broad, or has gotten more broad over time. And so we're going to look at them in a similar way. The one that we're really going to talk about is the second one. That's going to be our most common sort of idea that we'll use. But I think that others are good just for you to be aware of. So Arrhenius acids and bases, which are the most simple, they only work in water. And the definition is that acids produce H+, and bases produce hydroxide. So in order for something to be a base, it has to have hydroxide ions. So scientists found that that wasn't quite a broad enough definition because there are some things that act like bases, like ammonia, that don't have hydroxide. And so the definition was broadened a little bit to this Bronsted-Lowry definition of acids and bases. As I said, this is the one that is sort of a nice happy medium for us. It's not too specific, but it's specific enough to encompass chemicals that we'll talk about. So, according to Bronsted-Lowry, acids donate hydrogen ions. So you're still having acids usually that start with H, with hydrogen. And here bases accept H+. And so in this case, you could have something like ammonia, which is NH3, grabbing an H+ from water and becoming NH4+. And so in this case, it's acting like a base because it's grabbing the hydrogen from that water. Lewis acids and bases are used a lot in organic chemistry. They work with a wide variety of substances. And in here, just like with Lewis structures, we're looking at electrons. So Lewis acids accept an electron pair, and Lewis bases donate an electron pair. We don't use that one very much. But if you go on and take organic chemistry, you will follow electron pairs all around. So here's just a little illustration of an Arrhenius acid. So it's a substance that produces hydrogen ions in water. And we say hydrogen ions just like to simplify, but what actually happens is that the hydrogen here is attracted to the lone pairs of electrons on the oxygen, and so it actually makes H3O+. Just for simplification purposes, we just call it H+, but really it's H3O. Hydronium it's called. So an Arrhenius base likewise produces OH in water, so NaOH, when it dissociates, makes sodium ion and hydroxide ion. Bronsted-Lowry acid, remember it's a proton or a hydrogen donor. and a Bronsted-Lowry base is a proton acceptor. And so if you're going to donate a hydrogen, that hydrogen has to go somewhere. And so that is how we get these sort of situations where we have always pairs of acids and bases working together. And so it's going to seem a little bit weird, but in these Bronsted-Lowry cases, water is actually going to act as an acid or a base. So here we have ammonia, which is a base. We have water, which in this case is acting as our acid. And what happens is the lone pair of electrons up here on the on the nitrogen are going to pull away the hydrogen from the water. Okay, so we get NH4 plus and OH minus. So you're still getting OH in your basic solution. It's just not being directly produced by the ammonia. Sort of a roundabout. These, since this is a weak base, only part of it is going to dissociate at a time. And so the reaction is going to kind of go back and forth, maintaining equilibrium, but back and forth. And so sometimes this reaction might go this direction. And when that happens, now the hydroxide is the new proton acceptor, the new hydrogen ion acceptor, to get us back to water. And now the ammonium has this extra hydrogen on it that it can lose and become NH3. So we call these things conjugate pairs. So the base and the conjugate acid, the acid and the conjugate base. They're conjugate pairs because depending on which way the reaction goes, it might act like a base or it might act like an acid as it goes one way to the other. So here are a couple just of examples of conjugate pairs. You'll see that the only difference between them is whether or not there's a hydrogen. And in this case, all of the acids are in red and all of the bases are in blue, or pink, I guess. Acids are in pink, bases are in blue. So you can see here it can donate the hydrogen, here it can accept the hydrogen. Here it's donated a hydrogen, here it can accept a hydrogen. So conjugate pairs. Here is just a little example of what happens with Lewis acids and bases. So the hydrogen ion that's coming from, let's say, HCl can accept this electron pair and then come into the bond. And here, the NH3 can donate an electron pair so the hydrogen can bond to it. So it's an interesting idea. Lewis, you know him from Lewis structures. So it's interesting that it's looking at electrons, same guy. But it's not, for what we do in this class, it's not a super necessary definition because it's really, really, really broad. Okay, last thing we'll talk about are neutralization reactions. And these you've actually done in the past. We just call them double replacement reactions. So it's the same idea. Basically an acid plus a base makes salt and water. So you can see here how it's double replacement. The H and the Na just switch places. You can get NaCl and HOH, which is another way of saying H2O. Down here, you can have MgCl2. Remember, you have to crisscross to get correct ionic charges. Well, so they add up to 0. Plus 2H2O. We just need a 2 there. And then balance your equations. H2SO4, same thing. You can get Na2SO4 and H2CO3. And we need 2 of these and 2 of these. Yeah. So we are going to talk a little bit more about neutralization when it comes to molarities. The important thing is that the moles of hydrogen ion and the moles of hydroxide ion has to be equal so they can completely neutralize each other. So in this, if we had 1 mole of HCl, we would also need 1 mole of sodium hydroxide. If it was something like this, we would need 2 moles of HCl for 1 mole of magnesium hydroxide. And so it's all calculations that we've done before. We're just looking at them in a slightly different way. And you also, when you do the titration lab, that will also look at the same concept, looking at the math of neutralization. So enjoy!